Uh, Hello everybody. Welcome to my lectures. And this is the first time that I'm writing a lecture, so please expect some mistakes. However, you should be warned that this lesson is not used until grade 12. This lesson is not for grade 8. It's not supposed to be discussed in grade 8 as well. So, today we'll be discussing and tackling upon the most powerful forms of generation of energy known as nuclear fusion and nuclear fission. This will only be a quick overview. As you can see on this figure over here, atoms, mainly hydrogen and helium atoms, seem to gather up in order to generate the energy. And this one, they also leave remnants such as decay particles, positrons, and neutrinos, which are something that we should tackle later on, which likely we may no longer meet anymore. So over here we can see that one neutron over here will enter a uranium-235 atom. This is a uranium, like what you see, that's a radioactive element over here. After that, one neutron will enter this uranium-235, so it can become uranium-236. However, it's unstable, so it's capable of triggering a fission. Therefore, this fission over here will allow you to generate energy as well as pressure from the fission product over here. And then, boom, creates gamma ray and more energy. Therefore, it can also be used for weapons. If you have a microfission reactor that's capable of generating this gamma ray and therefore creating some sort of railgun made out of nuclear fission. That's funny. Yeah, it also releases energy and gamma rays. So the remaining neutrons can also be used for chain reactions, and therefore some materials are known as fissile. Fissile materials are also capable of, creating chain reactions. Even though if it's fissionable, it may not be fissile, so it does not support chain reactions. Now, I'll give you some quick facts about nuclear fusion and nuclear fission. So the two main elements for nuclear fusion are hydrogen, the water, and helium, the air. Nuclear fusion is also what makes stars shine bright. That means that you see like the sun over there. The sun is currently using nuclear fusion. I don't know in other dimensions, they may not use nuclear fusion, but, well, it's a mystery because it's we are in our universe. Okay. So, in order for atoms to fuse, they need to be around 100 degrees C. 100,000 C, actually. In order for atoms to fuse, they must be 100,000 degrees C in order to break the Coulomb barrier. Sorry for the 100 degrees C. That's the boiling point. I mean, the fusion point is 100,000 degrees C. Which means that we need to heat up water in here to 100,000 degrees Celsius in order for it to break the Coulomb barrier and therefore atoms. This is done with fusion reactors actually. The fusion reactors also have powerful magnets, so they'll be able to redirect the hydrogen and helium atoms that they're able to fuse, therefore allowing it to generate energy. However, it needs to be heated up first by a machine known as the tokamak. Tokamaks is a donut-shaped machine that allows you to heat up water all the way to 100,000 degrees Celsius, and therefore allowing you to break the Coulomb barrier, and therefore allow atoms to fuse. Yes. Also, nuclear fusion. Some stars cannot fuse, so they're called brown dwarfs. Those are called brown dwarfs. Some others don't fuse at all, so they become gas giants. Yeah, gas giants would have been stars. However, they weren't dense enough, so they weren't hot enough as well for nuclear fusion. So they become storms. One over here is that nuclear fusion is what makes certain bombs extremely powerful by releasing the energy and the pressure to release hundreds of thousands to millions or even hundreds of millions of tons. Therefore, nuclear fusion when detonated, will release kilometers, has a blast radius of kilometers, tens of kilometers actually. The most powerful thermonuclear weapon would be the Char Bomba, which is around 50 megatons, followed by the Casper Bravo, which is also from United States. Char Bomba is from Russia, hence the word char. Oh, it's a bit awkward, but whatever. So, 15 megatons. Also, did you know that in the movie Back to the Future, you're able to use junk, and then fuses the atoms of that piece of junk, so you'll be able to form energy. Yeah, because sometimes they may have any water content, so therefore it becomes liquidified, and therefore it becomes water. It's heated up, and therefore it becomes fuel, and it releases the other remaining elements of it. So that's it for nuclear fusion. Nuclear fusion is fusing atoms so they'll be able to become energy. They fuse into a denser atom to become. Now let's encounter and tackle nuclear fission. So the simplest way to describe nuclear fission is that letting a neutron, or putting a neutron inside a uranium-235 isotope, or simply uranium, we need to insert a neutron in the uranium, and therefore it becomes a denser version of uranium known as the uranium-236. However, this is a bit unstable, so it can cause fission at any time. Therefore, it will trigger nuclear fission, in which nuclear fission will release a lot of energy, as well as fission products and decay. Energy is also delivered in the form of fission products, as I said before, as well as gamma rays. So powerful gamma rays are allowed to generate a lot of energy, but some gamma rays may be delayed. So after fission, it will also release other particles such as decay particles and positrons, neutrinos, and other forms of energy. Especially neutrinos. They're usually the heat that we would experience way over the sun. So that's why they could also be converted to energy. That's why the sun, the solar light, can also be converted to energy because of the ultraviolet light. Therefore, ultraviolet light is a bit less than that. Well, actually, is a bit less than compared to that of gamma rays. However, they'll be extremely powerful still if you use a lot of them via solar panels. So it creates a photovoltaic effect, and therefore allows you to create a current of electricity. However, in order to support okay, so after that, sorry guys, you can also do a chain reaction, because due to the fact that fission will also release neutrons, which can be used for more chain reactions because of how neutrons are required in order to cause a chain reaction or even fission. And neutrons are required in order to trigger fission. So therefore, we could use chain reactions. Therefore, we'll be able to support fission chain reactions by putting some fissile isotopes such as uranium-235 and plutonium-239. And like fusion, it is used to generate tons of energy, and therefore it's combined, and therefore it could be used to couple on with nuclear fusion from a thermonuclear weapon. Therefore, combining fission and fusion is just insanity. Yeah, I couldn't remember. As you can see, this here. We add one neutron to uranium-235, and then it becomes uranium-236, and fission occurs. Therefore, it becomes barium-144 and proton-89, and some gamma rays, 3 neutrons for chain reaction, and decay particles. Also, this is a Back to the Future reference. Plutonium can generate 1.31 gigawatts when fission occurs. That's a Back to the Future reference as well. Yes. So this is my discussion and my lecture. Hopefully you've understood it. I only got 10 seconds to finish it. So thank you very much, and see you later. And have fun fusing stuff.